So this module is about multivariate data analysis, and most of the time our data is going to come in the form of a matrix. And so we're going to spend a bit of time now thinking about matrices, thinking about the building blocks of matrices and the properties of matrices. Okay. So the basic situation is we've got some matrix A. Let's suppose it's an n by p dimensional matrix. So that means it's got n rows and p columns. And we might call the individual elements lowercase a, I, j. And sometimes it will be useful to think about this matrix A in terms of its columns. So we might think about column 1, column 2, up to column P, which has got P columns. Whereas other times we might think about it in terms of rows. Okay, so it's got n rows, so we've got the first row R1, second row R2, these are vectors of course, okay, and the last row Rn, it's got n rows. So the columns are vectors, column vectors, the rows are row vectors. Okay. So a few important matrices that we'll rely upon throughout, and I won't highlight them all now, but just to pick out a couple. We've got the identity matrix, n say, so that is the n by n matrix which has 1s on the diagonal and it has 0s off diagonal. Okay, so I might just sometimes write that as a big 0 to indicate all the elements off the diagonal are 0. The other thing that might be useful is the diagonal elements where we specify the diagonals. So we might say things like the diagonal element with elements 1, 3, 2, say. So that is a 3 by 3 matrix which has 1, 3, 2 on the diagonals and 0 off diagonal. So I'm going to assume that you know all the usual things like how to add matrices, how to multiply matrices, how to multiply them by a scalar, and so on, and that you know all the rules of addition and multiplication for matrices. I'm also going to assume that you know about the transpose of a matrix, which is, I'll denote as A transpose, A to the power of a T, A transpose, and the trace of a matrix. So the trace of a matrix A is just the sum of the diagonal elements, sum from A, I, summed over I. And I'll assume you know basic facts about transposers as well. So I'll assume that you know that if A and B can be multiplied, that the trace of A times B is the trace of B times A, etc. For square matrices, so if A is n by n, we often talk about the inverse of the matrix. I'll assume you know about them as well. Okay, so if A has an inverse, we have that A times A inverse is the same as A inverse times A, and that is the identity matrix. Finally, I'll assume you know about determinants. Okay, so we'll write the determinant of A. We won't have to compute these ourselves, but I assume we know something about their properties. So we know that, for example, determinant of A times B is, assuming A and B are both square matrices, it is the determinant of A times the determinant of B. Okay, so the right way to think about matrices is as linear transformations between different vector spaces. So if A is an n by p matrix, we can view it as a map, as a linear transformation between two vector spaces. Okay? So between Rp and Rn. Okay, so A is a map from Rp to Rn. So let's suppose we're using the basis V1 up to VP for RP. Then any vector V in RP, I'm sorry, I've been forgetting to underline my vectors. I'll try to remember to do that. But okay, so any vector V in RP can be written as a linear combination of these basis vectors. So V must be the sum of lambda I times bi, I equals 1 up to p. So if we're going to write V as a vector of coordinates with respect to this basis, we'd write that V is lambda 1, lambda 2 down to lambda p. Okay, so that's the vector V represented in coordinates relative to this basis V1 up to VP. So let's suppose we're using basis W1 up to Wn for Rn. So how then do we represent the linear transformation A as a matrix relative to this basis for the input space Rp and the output space Rn? Well, it's very simple. We have that A times Vi, where Vi is one of our basis vectors for Rp. Well, this must be a linear combination of the W's, which are a basis for Rn. So we know A times Vi must be an Rn, because A maps from Rp to Rn. So let's write this as A1I W1 plus A2I W2 plus dot 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 plus ANI WN. Okay. And similarly for the other basis vectors. Okay. So we think about AVI giving us the ith column of A. Then all we have to do for any arbitrary vector to work out A times V is multiply the matrix A, where the columns are given by these terms, and that will tell us the coordinates of AV in the basis for Rn. So AV gives the coordinates with respect to basis W1 up to Wn. So I want to just think about the basics for a minute and think about a matrix multiplied by a vector. So a matrix vector product. So suppose A is an n by p matrix and X is a p by 1 vector. So you probably think of a matrix times a vector in terms of the inner product of the columns with the vector. Okay, so you probably think of this as x1 plus 2x2, 3x1 plus 4x2, 5x1 plus 6x2. Okay, and that is of course how we work out this matrix times a vector. But arguably it's better often for this module to think about it in terms of a linear combinations of the columns of A. So instead of thinking about it in these terms, we could think about this as x1 times the vector 1, 3, 5 plus x2 times the vector 2, 4, 6. So this emphasizes that a matrix times a vector is another vector, and it leads us to the concept of the column space. To the column space of a matrix. So the column space of A is the set of all linear combinations of columns of A. Okay, and we write this often as C of A, the column space of A, are all those vectors A times X, where X is any possible input vector, so a vector in RP. So it's a set of all linear combinations of the columns of A. So for the matrix above, for the choice of A above, we have that the column space of the matrix 1, 2, 3, 4, 5, 6. Well, that's just the span of the vector 1, 3, 5, and 2, 4, and 6. Now let's consider another vector. So let's consider B. Let's suppose B is 1, 3, 5, 2, 4, 6, just as before. But now let's add a couple of extra rows. Okay, so let's say 3, 7, 11. So just add the first two columns to give us a third column. And let's have one more. Let's just multiply the first column by 2, say. 2, 6, 10. So what's the column space of B? Well, the column space of B is exactly the same. Okay, this column was the first column plus the second column. This column was 2 times the first column. Okay. So the linear combination of columns in B is exactly the same as the linear combination of columns in A. I've not actually expanded the space at all. So in other words, the column space of B equals the column space of A. The dimension of the column space of A is the number of linearly independent columns of A, and it's called the column rank. So note that in this case the column rank of A is 2, and we also said that's the column rank of B. Now we can also think about the row space of A. Okay, so we won't use this notation but very often, but the row space of A is, let's say, R of A, which is the set of vectors of the form X transpose times A, just a linear combination of the rows of A. So that's for any vector X which is in R n. And I think it should be fairly obvious that this is the same thing as the column space of A transpose, in that if I think about the rows of A, if I transpose A, I get the rows now become the columns of A transpose. So a key kind of theorem in linear algebra is how the row rank, so that's the dimension of the row space of A, relates to the column rank of A. Well, let's think about that. Let's just do it by demonstration. Let's say if R is the column rank of A, then we can pick a set of R linearly independent columns from A, and I'm going to put these together in a matrix C, so, and form a matrix C. Okay, so it's just some of the columns of A that are linearly independent. So it's R columns. This is an N by R matrix. So each column in A must be a linear combination of the columns in C. So we can write A is C times R, where R must be an R by P matrix. So for example, we had B before, and we said that this is formed from just two columns. So let's let our matrix C be 1, 3, 5, 2, 4, 6. So they are linearly independent. So that's going to be our matrix C. And now we have to write down the matrix R, which tells us how many combinations of each column to make each of the columns in B. So for the first column here, we need one lot of the first column in C. So we need a 1 and a 0. To make the second column in B, we take one lot of the second column in C. So that's 0, 1. To make the third column, we take one lot of the first column plus two lots of the second column. So it's going to be a 1, 1. And the final column is just 2 times the first column. So that's going to be a 2 and a 0. So this is our matrix R. So the dimension of R must be R times P, as we said. But A equals CR, so C is N times R, R is R times P. So A equals CR shows that the rows of A are a linear combination of the rows of R. So it shows that the rows of A are a linear combination of the rows of R. So from this we must have that the row rank of A can be at most R, because we've used R rows in capital R. We've taken linear combinations of them to make all the original rows in A, so that its row rank must be at most R. And R, remember, is the column rank of A. Now this is true for any matrix. We're not doing anything special here. So it's also true for A transposed. So we have that the row rank of A transposed is less than or equal to the column rank of A transposed. Well, now, what is the row rank of A transposed? Well, that is just the column rank of A. And what's the column rank of A transposed? Well, that is the row rank of A. Okay. And we've already proven the row rank of A must be less than the column rank of A. So we get that the column rank equals the row rank. This is one of the kind of fundamental theorems in linear algebra. So because the column rank equals the row rank, we just refer to the rank of matrix. So we can just refer to the rank of a matrix. Okay. So back to our example, we have that the rank of the matrix B is 2. So this now puts us in a position to think about the major subspaces associated with the matrix A. Remember that we think of A as a map between vector spaces, so between Rp and Rn, if A is n by P matrix. So in other words, X goes to A times X. Well then, one of the subspaces associated with A, we've already talked about, but we'll give it a different name. We'll talk about the image of A is, what it is, image of A, and that is the set of all vectors 8 times x for any vector x. Of course, we've already seen this space. We called it the column space. The other space is called the kernel or null space of A. So the kernel or null space of A is, let's say, the kernel of A. Well, that is the set of all vectors x such that A times x is 0. And this is a subset of our space Rp. The rank nullity theorem tells us about the relative dimensions of image and kernel of a matrix. So the rank nullity theorem says that the dimension of the image of A, which is the column space of A, plus the dimension of the kernel of A is the space, the original vector space P. Similarly, A transpose is a map from Rn to Rp. So again, the rank nullity theorem gives us the dimension of the column space of A transposed plus the dimension of the kernel of A transposed is n, because A transpose is a map from Rn. Well, we know that the dimension of the column space of A is just the rank of A. And similarly, we know that the dimension of the column space of A transpose is the dimension of the row space of A, or again, just the rank of A. So what we've got is that the rank of the matrix A plus the dimension of the kernel of A is P, or that the rank of A plus the dimension of the kernel of A transposed is n. So one question we might want to answer is, when does Ax equal y have a solution? Okay, so suppose someone comes along and gives you A and gives you y and asks you to find x. When does that have a solution? Okay. Well, it has a solution precisely when y is in the column space of A. So there exists x in Rp such that Ax equals y if y is in the column space of A. So when is it a unique solution? Well, suppose there are multiple solutions. Suppose Ax equals Ax prime equals y. So first x and x prime not equal to each other. Suppose there are two solutions or many solutions. Well, x and x prime are in the same vector space, so we can write x prime as x plus another vector u. So we must have that Ax prime is Ax plus Au, which is y, and we know that Ax prime is equal to y. Okay. So this must tell us that Au is 0. Okay. So U is in the null space of the matrix A. So it's in the kernel of A. So the equation AX equals Y has multiple solutions only if the dimension of the kernel of A is bigger than 0. So AX equals Y has multiple solutions only if the dimension of the kernel of A is bigger than 0. If the dimension of the kernel is 1, then we have a line of solutions to AX equals Y. If the dimension of the kernel is 2, we have a plane of solutions, and so on. So just finally, suppose that A is a map from Rp to Rp, so that A is a P by P matrix. Okay? When does A have an inverse? Okay, when there's a matrix A inverse, such that A times A inverse equals identity. Well, it has an inverse precisely when the kernel of A is equal just to 0, contains only the matrix 0. Okay, so the dimension of the kernel of A is 0. Okay, so in this video we've seen some notation for matrices. We've thought about the column space and row space of a matrix, leading to the idea of a rank of a matrix. And we've seen the rank nullity theorem. Okay, so some tasks then. Let's suppose you're given the matrix A, that 1, 0, 3 in the first row, 0, 2, minus 4 in the second, 1, 1, 1 in the third row. What is the rank of A? So you can think about the column rank or the row rank, and we know they're the same. What is the rank of A? Then, can you describe the column space of A? What's its dimension? And what vectors span it? Can you give a vector space, a basis for A? Find the matrix in the kernel of A, and thus describe the kernel of A as a vector space, giving a basis for it. Finally, is the matrix A invertible? Then, what is the determinant of A?